Section 10.3 talks about phase transitions. So going from the liquid phase to the gas phase, or the gas phase to the liquid phase. And just to review, we have a few terms. If you're going from liquid to gas, that can be called vaporization. It can also be called evaporation. And then if it's all happening at once, we can even call that boiling. So boiling is like evaporation, only a lot faster. The opposite, going from gas to liquid, would be called condensation. Then we have liquids that evaporate easily being called volatile. Liquids that don't evaporate easily would be called non-volatile. So I'll go ahead and show you that figure in the textbook in just a moment. But even when a liquid is a liquid, above the liquid there are a certain number of molecules that are floating around in the gas state. And that's, especially in a closed system, that would be in equilibrium. So if you have a bottle that's closed and you have some water and some ethanol liquid in the bottle, then there's a little bit of water and a little bit of ethanol or alcohol in the gas phase above the liquid. Even if it's not at the boiling point, there's still a little bit of that in there. And if you open a bottle of alcohol, you can usually smell the alcohol because it's a little bit in the gas phase as well. And the more volatile a liquid is, the higher the vapor pressure is, because again, that means it's evaporating easily, and so more of the molecules are in the gas phase. It doesn't have to be at the boiling point temperature, of course, but if it is warmer, if there's a higher temperature, if this bottle is warmer, you're going to smell that alcohol more strongly because it has a higher vapor pressure at a higher temperature. There'll also be more water as well. You just don't smell that as easily, but there's just going to be more molecules in the gas phase when there's a higher temperature. I just thought I would call your attention to these figures in your textbook that are mentioned in the note packet. So this is an illustration of the vapor pressure of a liquid. The liquid is put into this sealed container, and some of the liquid molecules escape into the gas phase. And then at a certain point we have an equilibrium reached. The system is closed, and so we reach a point where the molecules that are going into the gas phase from the liquid, that rate is equal to the rate at which the gases are going back to liquid phase. So we have some liquid molecules becoming gas, some gas molecules becoming liquid, and when both of these are occurring at the same rate, then that's an equilibrium. The state is not changing at that point, and you can measure the pressure of the gas phase, and that is the vapor pressure that is above that liquid. And this is dependent on temperature, because at higher temperatures there are more molecules that have enough energy to escape from the liquid phase and become the gas phase. I mean, it takes more energy for something to be, for a molecule to be bouncing around in the gas phase than it does for the molecule to be in the liquid phase. That's why when you heat things up, they go from liquid to gas, they boil, because it takes more energy to be a gas. And at higher temperatures, these liquids have more molecules that have enough energy to become a gas. So the vapor pressure increases at higher temperatures. If you keep increasing the temperature, you reach a point where the vapor pressure increases and increases so much that the vapor pressure actually equals atmospheric pressure or the surrounding pressure. And when that happens, then all of it can vaporize, not just the ones that are slowly escaping from the surface. And that is called boiling. So the boiling point of a liquid depends on the pressure that's around that liquid. If you have 1 atmosphere of pressure around water, then it will boil at 100 degrees Celsius. However, if you have a lower atmospheric pressure, like you might at high elevations, maybe if you're in a town in the mountains, you might have a lower atmospheric pressure, and that will make the vapor pressure of water reach the atmospheric pressure or the surrounding pressure at a lower temperature. And so you have a lower boiling point of water at that lower pressure. That's why if you sometimes read instructions for a cake mix or something, they will have high altitude cooking instructions to account for the fact that water boils at a lower temperature. And so a lot of times you have to increase the cooking time of something. If you're going to be boiling it in water at 95 degrees Celsius, it's going to take a little longer to cook than if you're boiling it in 100 degree Celsius water. I also encourage you to watch the video that I have, the outside video, where someone is boiling water with ice. So they are effectively putting water under vacuum and decreasing the pressure so that it boils at a lower temperature. So the boiling point of a liquid depends on the pressure. We do have to list boiling points sometimes in reference tables, and so we will call something the normal boiling point is the temperature that it boils at when we have a standard pressure of 1 atmosphere around that liquid. It turns out that the vapor pressure of a liquid is related to the enthalpy of vaporization, or the energy, the thermal energy needed to vaporize a substance is related to how many molecules will enter the gas phase at any given temperature. And so this vapor pressure has a constant that's dependent on the identity of the substance. It also has the enthalpy of vaporization, which changes with different substances. So a lot of times this equation is rearranged to just compare two vapor pressures at two different temperatures for the same substance. Then that constant A will cancel out and we won't need to know what that constant is. So the form of the Clausius-Clapeyron equation that we are going to be using is that the natural log of the ratio of one pressure to another is the enthalpy of vaporization over R, the ideal gas constant, times 1 over one temperature minus 1 over another temperature. So what we can do with this equation is figure out how a boiling point changes with different pressures around it. So let's go ahead and try to do this problem and figure out for ethanol, where the normal boiling point is 78.4 degrees Celsius, what is the boiling point at a high elevation when the atmospheric pressure is not 1 atmosphere, but it is reduced to 0.885 atmospheres. And remember, we said when you reduce the pressure, that also reduces the boiling point. So we're going to make a prediction here that it is less than 78.4 degrees Celsius. When we do this equation, we are going to have the temperatures in Kelvin. And the heat of vaporization, which might be given in kilojoules per mole, you need to change to joules per mole and use the R value that has joules in it so that that will cancel as well. So our normal conditions, our normal boiling point T1 is 78.4 degrees Celsius when the pressure is 1 atmosphere. So that's why this is the normal boiling point temperature, because this is the normal atmospheric pressure. Of course, we have to change this to Kelvin. So we have 351.6 Kelvin. And then P2 is going to be 0.885 atmospheres. And T2 is what we're looking for. And then the heat of vaporization, the enthalpy of vaporization is 38.56 kilojoules per mole, which is 38,560 joules per mole. So we need that value as well. So the natural log of P2 over P1 is this heat of vaporization in joules per mole divided by R with these units, 8.315 joules per mole Kelvin times 1 over T1 minus 1 over T2. On this side of the equation, the atmospheres cancel, and the natural log of 0.885 is negative 0.122. On this side, we have joules canceling and moles canceling. And so we have 4,637 Kelvin times 1 over 351.6 Kelvin minus 1 over T2. Then if we divide both sides of this equation by 4,637 Kelvin, then we get this side with just the 1 over 351.6 Kelvin minus 1 over T2. So this ends up a pretty small number, 0.0000263 inverse Kelvin, or Kelvin to the minus 1. And then we still have this same right-hand side. So let's go ahead and add 1 over T2 to both sides. So then that makes the equation look like this. 1 over T2 minus 0.0000263 inverse Kelvin would be this. Now let's add 0.0000263 inverse Kelvin to both sides. And let's go ahead and divide 1 by 351.6 as well, which is 0.002844. And that's inverse Kelvin. We're going to go ahead and add this 0.0000263 inverse Kelvin. And that adds up to give 0.002870 inverse Kelvin. So now we have to just flip each side. I'm going to go ahead and do this at the top because it's getting crowded here. So what I'm doing here is flipping both sides of the equation. I'm going to put T2 in the numerator. So I'm going to flip that. And then I'm also going to flip this side. So we have 1 over 0.002870 Kelvin to the minus 1. That's going to make this a regular Kelvin for the units. And it becomes 348.4 Kelvin. And that is also 75.2 degrees Celsius. And this is less than 78.4 degrees Celsius, so our prediction is correct. Also, it's not a lot less, so that's encouraging. We don't want something really crazy. It's just a small decrease in the atmospheric pressure, and so we have a small decrease in the boiling point. So that makes sense. We've already mentioned and used this enthalpy of vaporization of ethanol. So let's make sure that we know what this means. This is the energy needed to take 1 mole of liquid ethanol and convert it into 1 mole of gaseous ethanol if we are already at the boiling point temperature of the ethanol. So if we have cold ethanol, we're going to have to warm it up first. We're going to need more than this amount of heat energy. But if we have liquid ethanol that's at the boiling point, ready to boil, this is how much it takes per mole to vaporize it. So doing this reaction to 1 mole of the ethanol takes 38.56 kilojoules. If you have a different amount, you can just use that relationship to convert it. If we have 0.762 moles of ethanol, we know that 1 mole takes 38.56 kilojoules. So this smaller amount will take fewer kilojoules of energy. It takes 29.4 kilojoules. What if we had our amount of ethanol in grams, which is not too unreasonable? So now we need this other relationship that the molar mass of ethanol is 46.07 grams per mole. Since we know our enthalpy of vaporization related to the moles of ethanol, let's go ahead and convert this to moles. And then we can use the information that 1 mole of ethanol needs 38.56 kilojoules of energy. So that amount of ethanol would take 53.1 kilojoules to boil. If you want, you can convert the enthalpy of vaporization into joules per gram. So this is our enthalpy of vaporization in kilojoules per mole. A kilojoule is 10 to the third joules, or 1,000 joules. So we can convert that to joules. And then a mole of ethanol is 46.07 grams. So multiplying by these conversion factors would give 837.0 joules per gram of ethanol that you want to boil. Besides changing into gases, another thing that liquids can do is turn into solids, and that is called freezing when a liquid changes into a solid. It's called melting when the solid changes into a liquid. So the melting and the freezing happen at the same temperature. It just depends whether you have something cold and you're warming up to that temperature and melting, or if you have something warm and you cool down to that temperature, then you can freeze something. So the melting point of ice is 0 degrees Celsius. The freezing point of water is also 0 degrees Celsius. If you are trying to warm up a solid and you are already at the temperature where it's ready to melt, then you need to put a little bit more energy in to do the melting itself. And that is called the enthalpy of fusion. Fusion is another name for melting. So it's kind of like the enthalpy of melting, but we call it the enthalpy of fusion. And this is on a molar scale. So 1 mole of solid going to 1 mole of liquid takes 5.02 kilojoules per mole. So if we don't have a mole, we can definitely figure out the amount of energy we do need. If we only have 0.408 moles of ethanol and it takes 5.02 kilojoules per mole, this ends up being 2.05 kilojoules to melt that amount. If we have the mass of ethanol instead, remember we need this molar mass. That will convert the ethanol to moles. And then we can use the relationship that 1 mole of ethanol takes 5.02 kilojoules. And we can figure out that this amount takes 9.57 kilojoules to melt. All right, in addition to having liquids go to gases or solids go to liquids, you can have something go from a solid directly to a gas. If you've ever encountered dry ice, then you know this. You don't have the solid carbon dioxide melt to be liquid carbon dioxide first. It goes directly to carbon dioxide vapor. The other direction, going from gas directly to a solid, would be called deposition. The most common example of that is in the wintertime. When you have some moist air in the morning, you might go and see some frost on a lawn, and that is, the grass didn't get wet and then freeze, because then it would look like a bunch of icicles. Instead, it looks frosty because the vapor, the water vapor, directly became ice crystals on the lawn. So going from a solid to a liquid, that energy change is called the heat of fusion, or the enthalpy of fusion. And then going from a liquid to a gas takes this amount of energy, the enthalpy of vaporization. So this is an example of Hess's law. We can add these two directly. If you wanted to go in 2 steps, you would need this amount of energy and this amount of energy, and it would take the same amount of energy to do it in 1 step. So if you wanted to go directly from a solid to a gas, the amount of energy, the heat of sublimation, would be the vaporization and the fusion added together. And so the last couple problems we've been working with ethanol. Just to refresh our memories, the heat of vaporization was 38.56 kilojoules per mole. The heat of fusion in the problem after that was 5.02 kilojoules per mole. And so that would make the enthalpy of sublimation equal to those two added together, which is 43.58 kilojoules per mole. So now we've been mentioning that to do this heating, to do this boiling, or to do the melting, those substances have to already be at the melting point temperature or the boiling point temperature. Back in chapter 5, we studied how if you add heat to something, the temperature can increase. So what happens to ethanol if you have solid frozen ethanol? You start here with solid frozen ethanol. If it's not yet at the melting point, then when you add heat, the temperature of that solid block of ethanol is going to increase. It's going to increase until you reach the temperature where the ethanol is ready to melt. So this area over here is where ethanol is a solid and it is increasing in temperature. Then when it reaches this temperature here, temperature G, that is the temperature at which the solid is going to start to melt. So that is the melting point. It's the same temperature as the freezing point, but we're heating it up, so we're mostly going to think about this as melting. So in this B area of the curve, the ethanol is not changing in temperature. See, this is the temperature, the y-axis here. The y value is not changing, it's flattened out. So at the same temperature, the whole time that heat is being added, this is where the solid is going to melt. So we're having melting. It's going from solid to liquid, and there's no temperature change. Once all the solid has melted, now in this area of the curve, the temperature is changing again, and we have this substance being a liquid. And this temperature can keep increasing until we reach another milestone temperature, temperature F, which would be the boiling point. You can't heat the liquid past this temperature. At that temperature, the liquid is going to boil. And in this area of the curve D, the temperature is not changing, but all the liquid is becoming gas. So the liquid is becoming a gas, which is boiling, and there is no temperature change at that point. Once all of the liquid has become vapor and we have a gas, then the temperature can keep increasing. So that's why steam burns are so dangerous, because, I mean, boiling water is bad enough, but boiling water can't get hotter than the boiling point. Steam can get hotter than the boiling point. So this is section E. This substance is a gas and the temperature is increasing. So hopefully this is understandable what this heating curve means. It's not a smooth line. It's not really a smooth curve. It's a bunch of line segments, because we have sometimes when the temperature is increasing and sometimes where the temperature has flattened out and plateaued. So it's kind of several curves actually in one, or several lines in one anyway. We can do a curve or a set of lines that shows the opposite direction where heat is being removed. So let's go ahead and plot temperature in degrees Celsius versus heat removed. So we're going to start at a very high temperature with ethanol being a gas, and then we're going to cool it down until it starts condensing. And this is going to happen at the boiling point temperature at 78.4 degrees Celsius. That's the transition between gas and liquid. Once all the ethanol has become liquid, then the temperature will decrease again until it reaches the point where the ethanol is going to become solid. And that is the melting point or the freezing point, which is negative 114 degrees Celsius. At that point, the ethanol will all freeze. Once you have frozen solid ethanol, then the temperature can start decreasing again and becoming even colder than negative 114. So in this area of the curve here, the ethanol is a gas. Here is where it's a liquid, and here is where it is a solid. This is where it's condensing. This flat area here and this flat area here is where it's freezing. Let's see if we can combine something that we've been working with recently, the heat to boil, the heat of vaporization, with something that we learned back in chapter 5, the heat that you need to raise the temperature of a substance. And since we don't have a smooth curve, this is going to be done in 2 separate steps, and then it's going to be added together. We need a certain amount of heat to do step A and a certain amount of heat to do step B, and so the total heat is going to be those steps added together. That's the total heat we need to do steps A and B. Okay, so we have ethanol starting at 25.5 degrees Celsius. So that is maybe around here. That is where ethanol is a liquid at room temperature. So we have liquid ethanol and we have it at 25.5 degrees Celsius. It needs to raise in temperature until it is 78.4 degrees Celsius, and then it needs to boil. So we need a certain amount of heat to get it up to 78.4. So this is step A, this amount of heat. And then we need some more heat to get it to all be a gas. And that is step B. And then the total heat added is going to do both of those steps, and that's A plus B. So back in chapter 5, we learned that the heat to raise the temperature of something is proportional to its mass, its specific heat, and the change in temperature. And our change in temperature here is 52.9 degrees Celsius. That's the change we want to cause. So our mass is 45.7 grams of ethanol. Our specific heat of ethanol is given to us here. It's 2.46 joules per gram degrees Celsius. And then our temperature change is 52.9 degrees Celsius. So this comes out to 5,947.1 joules. There's some more digits over here. We really only have 3. I'll go ahead and underline that so that when we add A and B, I can have the proper place value. So we are trying to boil now the 45.7 grams of ethanol. We are given the heat of vaporization in kilojoules per mole, not kilojoules per gram. So let's go ahead and convert this to moles. And so our molar mass of ethanol from earlier is 46.07 grams per mole. And this is 38.25 kilojoules. We only have 3 significant digits because of the mass of ethanol, so I'll go ahead and underline that also. Now this one is in joules and this one is in kilojoules, so I will go ahead and convert the joules to kilojoules. That way we'll be able to add them together for step C. So when we add the heat needed for step B with the heat needed for step A, we get 44.1971 kilojoules, but that has too many digits. We only know 38.25 to 1 past the decimal. We know this other value 2 past the decimal. We're going to have to round this to 1 past the decimal. So altogether, we're going to need approximately 44.2 kilojoules to both warm it up and boil the ethanol. All right, let's try one more problem like this with some water. So we have ice, and we are going to take that from negative 18.2 degrees Celsius to a positive 36.8 degrees Celsius. However, we cannot heat ice up to 36.8 degrees Celsius because it will melt at 0. So what we're actually doing is we're heating ice from negative 18.2 degrees Celsius to 0.0 degrees Celsius. So that is step A. And then step B, the ice is going to melt. And then we are going to heat the resulting water from 0 degrees Celsius to 36.8 degrees Celsius. So the amount of heat to change the temperature of something is the mass times the specific heat times delta T. So we have 33.7 grams as our mass. Ice has a different specific heat than water. It's actually 2.027 joules per gram degree Celsius. So that's interesting that it's a little bit different from water. And then our change in temperature, our final temperature of 0 minus our initial temperature of 18.2 degrees Celsius is actually a positive 18.2 degrees temperature change. So we have 18.2 degree Celsius increase in temperature. And that gives 1,243.2 joules with 3 significant digits. To melt the ice, we need the heat of fusion. This time the heat of fusion is given in joules per gram, so we don't have to convert the grams into moles. We don't have kilojoules per mole, we just have joules per gram. So this is just the mass times the heat of fusion. So we have 33.7 grams of ice. That takes 334 joules per gram to melt. So that is 11,255.8 joules, again with 3 significant digits. And then for step 3, this is also a temperature change. So that's the mass times the specific heat times the temperature change. So that's 33.7 grams times the specific heat of liquid water, 4.184 joules per gram degrees Celsius. And then our temperature change, our 36.8 degrees Celsius minus the 0 degrees Celsius is a positive 36.8 degrees Celsius temperature change. And that ends up being 5,188.8 joules, again with 3 significant digits. So we want the total heat for all 3 of these steps. We want to do all 3 of these steps, heat the ice, melt the ice, and heat the water. So we need to add together these 3 amounts of heat. And when I add them, I get 17,687.8 joules. 2 of these are known to the tens place, and 1 of them is only known to the hundreds place. So we should really round this to the hundreds place, to 17,700 joules, or if we want to say 17.7 kilojoules, that would be the total amount of heat needed.